all, I would like to thank the organizer for this very interesting meeting. Essentially, what I speak is a joint work with Arnaldo Nanenter and Daniel Valezin from Groningen University. I will consider one problem in long-range percolation. In principle, let's consider this graph. Essentially is ZD, the hypercubic lattice, but the set of bonds, we have bonds with all lengths, but only bonds parallel to the coordinate axis. That is, for example, the ordinary Z2, and you have bond with length 2, with length 3, and so on. And it's also given some sequence, pi, where pi is the probability of some bond with length I is open. Then consider some independent Bernoulli percolation on this graph with this family of parameters. And as usual, I would denote by 0 connect to infinite the set of configurations such that the origin is connected to infinitely many points with open paths. Okay? What's the truncation question? For each k, let's consider this sequence, the truncated sequence in k. Essentially, is the same sequence pi if I is less than k, and is 0 if I is bigger than k. Essentially, we are erasing all bonds with length bigger than k. Then the truncation question is the following. Suppose that for this sequence pi, there is percolation with positive probability, then is it true that there exists some large k such that it still percolates with the truncated sequence? That is, the infiniteness of the range is indeed crucial for occurrence of percolation. Is it clear, the question? And concerning this question, there's a lot of works. Maybe the first work in this direction is a paper of Ronald Mester and Jeff Stife in 1996. If the sequence decays exponentially and there is percolation, then you can truncate it. Okay? The second work that I would like to mention is a work of Donata Surgailis, Vladas Sidoravicius, and Mario Lalliavaris. They consider some anisotropic model on Z2. If the horizontal bonds decays like this, 1 over n log n, and the vertical bonds are open with probability epsilon, we have only nearest neighbor in the vertical direction, then you can truncate it. Later, I think it was the thesis of Berger. He proved a lot of results, but among of these results, he proved that if the sequence Pn is at least 1 over n to the power alpha with alpha in this interval, then you also truncate it. And later, we have a sequence of papers, the first one with Sasha Friedl and Vladas Sidoravicius. We proved that if lim sup of the sequence Pn is positive, we can truncate it. The second one with Sasha. Here, our hypothesis is more general. Essentially, is no hypothesis. It's only the divergence of the series of Pn. Then we can truncate it, but this result is true only if d is at least 3. Indeed, with this hypothesis for d equals to 2, this is still an open question, if I can truncate it or not. And toward this, to solve this conjecture in 2 dimension with Artem Sapoznikov, we give another step. Essentially, this hypothesis says that if you are in the origin, the shortest bond, the shortest open bond starting from the origin has finite expectation. feature in all of these papers that none of these results work for oriented percolation. And now I will do a short break. In the case d equals to 1, the answer for the truncation question is no, because if you are in Z, for any k positive integer, if I divide in blocks with size 3k, let's say for example 0, 3k, k, 2k, the probability of all bonds starting from some vertex in this middle third, it has positive probabilities, so I have infinitely many, by what I can tell you, have infinitely many intervals like this with all bonds are closed. Then, if I truncate it, there's no percolation. And it's not related to the truncation question, but concerning long-range percolation in one dimension, maybe not the most important, but some seminal paper in this direction. It is Newman and Schulman paper. They consider a long-range percolation in Z when Pn is like this. And in this paper, they prove the following. If S is bigger than 2, there is no percolation. Well, it's trivial that if S is at most 1, there is percolation, by what I can tell you. If S, yes, if S is between 1 and 2, there's percolation for beta large. Essentially, it's a counterpart of this classical Dyson result about the hierarchical Ising model. And if S is 2, the behavior is a little bit different. If S is 2, there's percolation if beta is at least 1, but P1, the probability of some nearest neighbor bond is open, should be close to 1. And in the same paper, they conjecture the following. Essentially, here, there's percolation as well, oriented percolation. But for S equals to 2, this result works only for oriented percolation, non-oriented percolation. And they conjecture if the same behavior is still true for oriented percolation. This conjecture is not an open problem anymore. It was solved almost 20 years later by Domingos Marchetti, Vlada Sidoravicius, and Maria Eulalia Vares. They gave an affirmative answer for this conjecture. Essentially, I would like to illustrate that in general, oriented percolation is easier than ordinary percolation, but there are some problems that we can prove percolation, but to prove oriented percolation could be difficult. And I'd like to mention to illustrate this fact in this problem of it's not a truncated question, but is a long-range percolation in one dimension. Then let's come back to the truncated question. Our main result, we consider this graph. This graph essentially is ZD times Z plus. Let's say we have a D spatial coordinates and one temporal coordinate. And the set of bonds is this. It's better. I draw a picture. Here's the origin. I have bonds is the probability of some bond starting from the vertex xn to the vertex x plus I times some coordinate axis until the temporal coordinate n plus 1 is open with probability pi, and we consider some independent Bernoulli percolation on this graph with this sequence of parameters. Then let's suppose again that the sequence Pn diverges. Then by Borel-Cantel's lemma, the probability of percolation is 1. Then we ask if the truncation question is, has some affirmative answer. That is, there exists some large k such that this probability is positive. Then our main result says the answer is yes, but that is, the probability, the sequence of Pn diverges, but we prove this theorem only if the dimension is 2 plus 1. Remember that d for me, the graph is zd times z plus. Essentially, this is a d plus 1 dimensional graph. Then the answer is affirmative. More than this, we can prove that, the probability of percolation goes to 1 when the truncation parameter goes to infinite. Let me do a very brief sketch of the proof. Of course, it's enough to prove this theorem in the hardest case, d equals to 2. And let's fix some beta such that p beta is positive, that is any range in the support of the sequence pi. And for each vertex in the graph, I will define this bifurcation event. We say that there's a bifurcation on the vertex xn if there exists two positive integers such that the bond from xn to x plus a in the first direction until the next level is open. From this vertex, there's another bond open. We have 3 open bonds. It's better I take a picture. This is a bifurcation event. That is, let's suppose that this is the vertex xn. Then this bond is open. This is this bond. Then starting from this here, we have this bond is open. Observe that this bond essentially is along the second coordinate direction. Okay? And this bond, the third bond, is along the first coordinate direction. This is a bifurcation event. And we can see that the probability of this event occurs is given by this expression, and by hypothesis as the sum of pi n diverges. And this probability goes to 1 when k goes to infinite. Okay. Now, observe that if the origin is connected to this vertex and there's a bifurcation starting from here, then the origin is connected to these 2 vertices. Okay? And another remark is that given two vertices of the graph, these events are independent if the temporal coordinate, the difference of the temporal coordinate is at least 2, or if the second spatial coordinate are different, because they use disjoint sets of bonds. Now, I will perform some dynamical construction. I will define some, consider now Z2 plus, this graph, Some vertex in Z2 plus I will define as red if and only if. For example, let's suppose that the vertex Mn is red if and only if in my original graph this vertex is connected to the origin and there's a bifurcation starting from here. Then, for example, in this picture, we have that this vertex. Now we have a Z2 plus. This vertex is red because here is connected to the origin and there's a bifurcation here. Here is red because this vertex is connected to the origin and there's another bifurcation here. Observe that with this picture, we cannot say nothing about this. For example, this vertex would be red if and only if there's some bifurcation starting from here. Okay? Now, it's only to follow the ideas of Grimmett and Marstrand. Essentially, is the first in this paper of Grimmett Marstrand about percolation of slab. The dynamical construction essentially is the first lemma of this paper. I will not give the complete details, but essentially we have two sequence of set of vertices A and B. AI is the set of the cluster of the red vertices in the ith step. And by construction, we can see that if there's a infinite red cluster in the renormalized graph, this graph with red vertices, then this implies that there is percolation in our original model. And this will percolate. Observe that when I collect some vertex, this vertex will be red independently of the past with probability at least gamma k. Remember, gamma k is the probability of there's a bifurcation starting from some vertex. And as this probability could be take close enough to 1, when k goes to infinite, then it's enough to take k large enough such that gamma k is strictly bigger than the percolation threshold for oriented percolation on Z2. Then this proves the theorem. Another variation of this theorem, we can consider this graph. This graph essentially is the hypercubic lattice, but I will split the set of the bonds in two types of bonds. The vertical bonds essentially is some bond from xn to xn plus 1. And the horizontal bonds, we have long-range bonds parallel to the first coordinate axis. And we consider some percolation model on this graph. But now we have, again, our sequence pi and some extra parameter epsilon. And in this model, each vertical bond is open with probability epsilon, and each horizontal bond is open with probability pi when I is the length of this horizontal bond. Then, again, with Daniel and Arnaud, we prove that for the at least 2, and for any epsilon, and for any sequence pi such that the sum diverges, we have that the probability of percolation goes to 1 when k goes to infinite. And this result generalizes our previous result with Sasha Friedli in the context of non-oriented and isotropic percolation. I have some 3 minutes. I'd like to mention another work with Caio Alves from Leipzig, Daniel Valezin, and also my colleague from Belo Horizonte, Marcelo Hilário. Now, my hypothesis is stronger. Lim sup of the sequence Pn is positive. Otherwise, now this theorem is true for d equals to 1. That is, when I say d equals to 1, my graph has dimension 1 plus 1. In this case, again, the truncation question has an affirmative answer for this graph, and another result in the same paper. Here, the graph G is this graph, and G star is the hypercubic lattice. Essentially, we can prove the same result for the hypercubic lattice using long-range bonds. Only on the horizontal and vertical bonds, we have only nearest neighbor with probability epsilon. Again, we have an affirmative answer for the truncated question, and this second result generalizes our previous result with Sasha Freidli and Vlada Sidoravicius for non-oriented percolation. A final remark, I'd like to emphasize that all of these results have their analogous statements for the long-range contact process. And okay, that's all.